13 billion miles from Earth, in a region of space so remote that the Sun appears as nothing more than an unusually bright star among millions. A spacecraft is detecting something that its twin never found. Voyager 2, humanity's second interstellar explorer, crossed out of our solar system's protective bubble in November 2018 and entered the space between stars. Its twin, Voyager 1, had made the same crossing 6 years earlier in 2012, becoming the first human-made object to reach interstellar space. Both spacecraft carry nearly identical instruments. Both were built by the same team of engineers at NASA's Jet Propulsion Laboratory. Both launched in 1977. Both have been traveling outward from the Sun for nearly half a century. But Voyager 2 carries one instrument that Voyager 1 does not. An instrument that was broken on Voyager 1 decades before it reached the boundary of the solar system. And that single instrument has revealed something about the space between stars that Voyager 1 was physically incapable of detecting. Something that has forced scientists to fundamentally reconsider what they thought they knew about the boundary between our solar system and the rest of the galaxy. Something that suggests the cosmos surrounding our Sun is structured in ways nobody predicted. If you want to understand what Voyager 2 found in interstellar space that its famous twin completely missed, and why this discovery is reshaping our understanding of our place in the galaxy, hit that like button and subscribe right now. This is a story about two identical spacecraft that entered the same cosmic ocean from different shores and found two completely different worlds. Let's begin. To understand what Voyager 2 detected that Voyager 1 could not, you first need to understand how these twin spacecraft differ despite being nearly identical at birth. Because the story of what Voyager 2 found is inseparable from the story of what Voyager 1 lost. And what Voyager 1 lost, decades before it reached interstellar space, turns out to be the single most important instrument for understanding the boundary between our solar system and the galaxy beyond. Both Voyager spacecraft launched in the summer of 1977, each carrying 10 sets of scientific instruments designed to study the outer planets and their moons. The instrument suites were identical. Camera systems for imaging, magnetometers for measuring magnetic fields, cosmic ray detectors for high-energy particles, plasma wave subsystems for detecting vibrations in charged particles, infrared and ultraviolet spectrometers for analyzing atmospheric composition, and a device called the Plasma Science Instrument, known as PLS, designed to directly measure the properties of ionized gas or plasma surrounding the spacecraft. Plasma is the fourth state of matter, distinct from solid, liquid, and gas. It consists of atoms that have been stripped of some or all of their electrons, creating a soup of positively charged ions and negatively charged free electrons. Plasma is extraordinarily common in the universe. More than 99% of all visible matter in the cosmos exists as plasma. Stars are plasma. The solar wind is plasma. The interstellar medium, the material filling the space between stars, is predominantly plasma. Understanding plasma is fundamental to understanding the universe. The Plasma Science Instrument on each Voyager was designed to measure the density, temperature, velocity, and composition of plasma encountered by the spacecraft. It could detect both the solar wind plasma streaming outward from the Sun and any interstellar plasma the spacecraft might eventually encounter beyond the solar system's boundary. The instrument functioned by collecting charged particles through a series of apertures and measuring their energy and direction of arrival. From these measurements, scientists could reconstruct the properties of the plasma environment surrounding each spacecraft with remarkable precision. On Voyager 1, the Plasma Science Instrument failed in 1980 during the spacecraft's encounter with Saturn. The instrument's sensors degraded, and by the time the spacecraft left the Saturnian system, the PLS could no longer collect reliable data. Engineers attempted repairs through software updates and operational workarounds, but the damage was irreversible. The instrument was effectively dead. For the next 32 years, as Voyager 1 traveled outward through the heliosphere, across the termination shock, through the heliosheath, and eventually across the heliopause into interstellar space, it did so without the ability to directly measure the plasma surrounding it. It was blind to one of the most fundamental properties of its environment. When Voyager 1 crossed the heliopause on August 25, 2012, the event was detected through indirect means. The cosmic ray subsystem registered a sharp increase in galactic cosmic rays. The magnetometer detected a change in magnetic field direction. The plasma wave subsystem detected oscillations consistent with a higher density plasma environment. From these indirect measurements, scientists inferred that Voyager 1 had crossed from the solar wind-dominated heliosphere into the interstellar medium. But they could not directly measure the plasma that Voyager 1 was now immersed in. They could detect its effects. They could infer its properties. But they could not measure it directly because the one instrument designed for that purpose had been dead for 32 years. On Voyager 2, the plasma science instrument survived. It continued to function through every planetary encounter, through decades of cruise through the outer solar system, through the crossing of the termination shock in 2007, through years of travel through the heliosheath, and right up to the moment of truth. When Voyager 2 crossed the heliopause on November 5, 2018, its plasma science instrument was active and collecting data. For the first time in human history, a spacecraft directly measured the transition from solar plasma to interstellar plasma. Not inferred, not estimated, measured, directly, in real time, with an instrument specifically designed for that purpose. And what that instrument measured did not match what scientists expected based on Voyager 1's indirect observations. Not even close. The first surprise came from the heliopause itself, the boundary between the solar system and interstellar space. The heliopause is where the outward pressure of the solar wind, the stream of charged particles continuously emitted by the sun, is balanced by the inward pressure of the interstellar medium, the plasma and magnetic fields that fill the space between stars. Think of it as the point where two weather systems meet. The sun's weather pushing outward, the galaxy's weather pushing inward. Where they balance, a boundary forms. That boundary is the heliopause. Voyager 1 crossed the heliopause at a distance of approximately 121.6 astronomical units from the sun. 1 astronomical unit is the distance from Earth to the sun, roughly 93 million miles. So Voyager 1 crossed the boundary at 121.6 times the Earth-Sun distance, approximately 11.3 billion miles from the sun. Voyager 2 crossed the heliopause at approximately 119 astronomical units, roughly 11.1 billion miles. That is approximately 2.6 astronomical units closer to the sun than where Voyager 1 crossed. In absolute terms, Voyager 2 crossed the boundary approximately 240 million miles closer to the sun than its twin. This difference might seem small against the vast distances involved, but it is highly significant. The two spacecraft are traveling in almost opposite directions. Voyager 1 is heading generally northward relative to the plane of the solar system, while Voyager 2 is heading generally southward. They are sampling the heliopause at completely different locations, separated by tens of billions of miles. Finding that the heliopause is closer to the sun in one direction than in another means the heliosphere, the sun's protective bubble, is not spherical. It is not even approximately spherical. It is asymmetric, compressed on one side, pushed inward by some external force that acts more strongly from one direction than from the other. That external force is the interstellar magnetic field. The magnetic field that permeates the space between stars is not uniform. It has a preferred direction, determined by the large-scale structure of the Milky Way galaxy and by the remnants of ancient supernova explosions that have compressed and distorted the local interstellar medium over millions of years. This interstellar magnetic field pushes against the heliosphere's southern hemisphere more strongly than against its northern hemisphere, compressing the bubble and pushing the heliopause closer to the sun in the direction Voyager 2 was traveling. This asymmetry was predicted by some models but not confirmed until Voyager 2 provided its measurements. The confirmation matters because the shape of the heliosphere determines how much protection our solar system receives from galactic cosmic rays, the high-energy particles that stream through the galaxy and pose radiation hazards to any unshielded object, including astronauts and spacecraft. A compressed heliosphere means reduced protection in certain directions. It means the shield is thinner on one side. It means the cosmic radiation environment within our solar system varies depending on which direction you look. This has practical implications for future long-duration space missions beyond Earth's magnetosphere. But the asymmetry of the heliopause was only the first of Voyager 2's revelations. The plasma science instrument's direct measurements of the heliopause crossing itself revealed something far more unexpected. Voyager 2 detected plasma leaking outward through the heliopause before the spacecraft had actually crossed it. This was not supposed to happen. The heliopause in standard models is a boundary. Inside it, solar wind plasma dominates. Outside it, interstellar plasma dominates. The two plasmas do not mix. They are separated by the boundary the way oil and water are separated by their different densities. Yet Voyager 2's instruments detected solar wind plasma that had somehow penetrated the heliopause and was escaping into interstellar space. The leaking plasma was detected in a layer approximately 1 astronomical unit thick, just inside the heliopause. In this layer, solar plasma and interstellar plasma coexisted in a mixing zone that models had not predicted. The discovery of this plasma leakage layer has profound implications for our understanding of how the heliosphere interacts with the galaxy. If solar plasma is leaking outward through the heliopause, then the boundary is not a clean, sharp surface. It is a porous, permeable membrane. Material crosses it. Energy crosses it. The heliosphere is not a sealed bubble protecting the solar system from the galaxy. It is a leaky container through which the solar system and the galaxy continuously exchange material and energy. This exchange means the heliosphere is a more dynamic structure than previously understood. It breathes. It flexes. It leaks. It interacts with its environment in ways that static models failed to capture. Voyager 1 could not detect this leakage layer because its plasma science instrument was dead. The indirect measurements from Voyager 1's other instruments were not sensitive enough to detect the subtle mixing of solar and interstellar plasma in the boundary layer. The phenomenon was invisible to Voyager 1. It required the direct plasma measurements that only Voyager 2's functioning PLS instrument could provide. This is the first major discovery that Voyager 2 made that Voyager 1 completely missed. Not because Voyager 1 was not there. It crossed the same boundary 6 years earlier. But it crossed that boundary blind to the very phenomenon that would turn out to be one of the most significant discoveries of the entire Voyager mission. The second major difference between the two crossings involved the nature of the transition itself. When Voyager 1 crossed the heliopause in 2012, the transition was sharp and dramatic. The cosmic ray count surged abruptly. The magnetic field shifted direction rapidly. The available indirect indicators all pointed to a fast, clean crossing. One moment Voyager 1 was inside the heliosphere. The next moment it was outside. The transition appeared to occur over a distance of just a few tenths of an astronomical unit. A remarkably thin boundary given the enormous scale of the heliosphere. Voyager 2's crossing told a different story. The transition was smoother, more gradual. The plasma science instrument showed that the solar wind speed decreased progressively as the spacecraft approached the heliopause. The solar wind did not stop abruptly. It slowed down, thinned out. It mixed with increasing amounts of interstellar material. The boundary revealed itself not as a wall but as a gradient. A zone of gradual transition where the character of the plasma changed continuously over a distance significantly larger than what Voyager 1's indirect measurements had suggested. This difference between the two crossings is scientifically remarkable. It means the heliopause does not have a single, universal character. It varies from place to place. In some regions, the boundary is sharp and well-defined. In others, it is diffuse and gradual. The heliopause is not a simple geometric surface like a soap bubble. It is a complex, variable boundary whose properties depend on local conditions, the strength and direction of the interstellar magnetic field, the density and velocity of the solar wind in that region, and the dynamic interactions between these factors. Understanding this variability matters for fundamental astrophysics because the heliosphere is not unique. Every star in the galaxy that produces a stellar wind creates its own equivalent of a heliosphere, called an astrosphere. The Sun's heliosphere is the only one we can study from the inside. Voyager's measurements of how the heliosphere's boundary varies from place to place inform our understanding of how astrospheres in general interact with the interstellar medium. This has implications for stellar evolution, planet formation, and the radiation environment around other stars where life might exist. The third discovery that Voyager 2 made possible involved the interstellar medium itself, the plasma that fills the space between stars. When Voyager 2 crossed the heliopause and entered interstellar space, Its plasma science instrument began the first direct measurements of the interstellar plasma from within it. Voyager 1 had entered this same medium 6 years earlier, but could only characterize it indirectly through magnetic field measurements and plasma wave observations. Voyager 2 could measure the plasma directly. Temperature, density, velocity, composition, the fundamental properties of the medium that fills the galaxy between its stars. The interstellar plasma that Voyager 2 measured was denser than most models had predicted. The density of charged particles in the immediate vicinity beyond the heliopause was approximately 0.039 particles per cubic centimeter. This might sound like an incredibly low number, and by terrestrial standards it is. The air you are breathing right now contains approximately 25 quintillion molecules per cubic centimeter. The interstellar medium is roughly 25 quintillion times less dense than Earth's atmosphere. It is an extraordinarily good vacuum by any earthly standard. But in the context of interstellar physics, 0.039 particles per cubic centimeter is significant. Some models had predicted densities as low as 0.01 particles per cubic centimeter. The measured value was roughly 4 times higher than these predictions. A denser interstellar medium means more material pressing against the heliosphere from outside. It means the heliosphere is more compressed than lower density models suggested. It means the cosmic ray flux entering the solar system through the heliosphere is modulated differently than predicted. It means the local interstellar environment is not the quiet, sparse void that simpler models described. Voyager 2 also measured the temperature of the interstellar plasma and found it to be approximately 30,000 to 50,000 Kelvin in the region immediately beyond the heliopause. This sounds extraordinarily hot, and in terms of particle kinetic energy, it is. But temperature in a plasma is not the same as temperature as we experience it on Earth. Temperature measures the average speed of particles. In a very sparse medium, even very fast-moving particles transfer negligible heat to any macroscopic object because there are so few of them. A cubic centimeter of interstellar plasma at 30,000 Kelvin contains so few particles that it would feel colder than the emptiest vacuum chamber on Earth. The temperature is high. The thermal energy per unit volume is negligible. This distinction between temperature and thermal energy density is one of the most counterintuitive aspects of space physics, but it matters enormously for understanding the dynamics of the interstellar medium. The interstellar plasma temperature measured by Voyager 2 was consistent with heating by the passage of shock waves through the interstellar medium. When the Sun emits a coronal mass ejection, a massive burst of plasma and magnetic field launched into space by violent solar activity. That burst travels outward through the solar wind and eventually strikes the heliopause. The impact generates a pressure wave that propagates outward into the interstellar medium, compressing and heating the interstellar plasma. Over billions of years, countless such impacts from our Sun and from other nearby stars have maintained the interstellar plasma at temperatures well above what its distance from any stellar energy source would otherwise suggest. The interstellar medium is not passively cold. It is actively heated by the cumulative violence of every star in the neighborhood. Voyager 2's plasma science instrument also detected something that Voyager 1's indirect measurements had hinted at but could not confirm. The interstellar medium in the vicinity of the heliopause is not uniform. It varies. Density fluctuates. Temperature changes. The magnetic field shifts in intensity and direction. These variations suggest that the local interstellar medium contains structures, regions of higher and lower density, warmer and cooler patches, threads of magnetic field concentrated along certain directions. The space between stars is not a featureless void. It is a structured environment with its own internal dynamics and its own internal weather. Voyager 1's plasma wave subsystem had detected a persistent low-frequency hum in the interstellar medium beginning in 2017, a steady background vibration in the plasma that was interpreted as the thermal oscillation of the interstellar medium at its baseline density. This hum provided indirect evidence of plasma density. Voyager 2's plasma science instrument provided direct evidence, confirming and refining the density measurements with greater precision and revealing variations that the indirect method could not detect. The comparison between Voyager 1 and Voyager 2's observations of the interstellar medium reveals something profound about the space surrounding our solar system. The two spacecraft entered interstellar space from different directions, at different locations, separated by billions of miles. They found different conditions, different plasma densities at their respective crossing points, different heliopause thicknesses, different transition characteristics. This means the interstellar medium is not the same in every direction around the Sun. It varies spatially. The environment surrounding our solar system is not symmetric. It is shaped by forces and structures that extend far beyond our Sun's influence. This asymmetry has been attributed to the local interstellar cloud, a region of relatively warm and dense interstellar gas through which our solar system is currently moving. The local interstellar cloud is approximately 30 light-years across and has been flowing through our region of the galaxy for millions of years. The Sun entered this cloud at some point in the past and will eventually exit it, entering a different region of interstellar space with different density, temperature, and magnetic field properties. The shape of the heliosphere, the protection it provides, and the cosmic ray environment within our solar system all depend on the properties of whatever interstellar cloud we happen to be passing through. The heliosphere is not a fixed structure. It is a dynamic response to ever-changing external conditions. As the Sun moves through different regions of the galaxy, the heliosphere expands, contracts, and reshapes itself continuously. Voyager 2's measurements of the interstellar medium have provided the ground truth that calibrates our understanding of this dynamic process. Without Voyager 2's direct plasma measurements, our knowledge of the interstellar medium would rest entirely on Voyager 1's indirect observations and on remote astronomical observations from Earth-based and space-based telescopes. Those remote observations, while valuable, provide averages over enormous volumes. They cannot detect the local variations that Voyager 2's instruments have revealed. The difference between remote observation and in situ measurement is the difference between studying the ocean from a satellite and diving beneath its surface. Both approaches provide valuable information, but only the diver can feel the currents, taste the salt, and measure the temperature at a specific depth in a specific location. The fact that Voyager 2 carries a working plasma science instrument while Voyager 1 does not is one of the great fortunate accidents of space exploration history. When Voyager 1's PLS failed in 1980, no one knew that the instrument would become critical for understanding the heliopause crossing more than 3 decades later. The failure seemed inconsequential at the time. The instrument had completed its primary mission of studying plasma environments around Jupiter and Saturn. Its loss was documented and accepted. No one anticipated that both spacecraft would survive long enough to reach interstellar space, let alone that the plasma measurements at the boundary would yield discoveries of this magnitude. The survival of Voyager 2's PLS through 49 years of operation in deep space, including exposure to cosmic radiation, extreme temperature cycling, and the vibration of spacecraft maneuvers, is an engineering achievement that borders on miraculous. But Voyager 2's discoveries extend beyond the heliopause and the interstellar medium. The spacecraft's unique trajectory through the solar system gave it a perspective that Voyager 1 never had. While Voyager 1 visited only Jupiter and Saturn before heading northward out of the solar system, Voyager 2 visited all 4 giant planets: Jupiter, Saturn, Uranus, Neptune. It remains the only spacecraft in history to have visited the ice giants Uranus and Neptune. Those encounters, conducted in 1986 and 1989 respectively, provided data that scientists are still analyzing and reinterpreting 4 decades later. The Uranus encounter was particularly significant because it revealed a planet unlike anything scientists expected. Uranus rotates on its side, with its axis of rotation tilted approximately 98 degrees from the vertical. This extreme tilt means the planet's poles alternately point directly at the Sun during its 84-year orbit. When Voyager 2 arrived in January 1986, the South Pole was pointed almost directly at the Sun. The planet's magnetic field was equally bizarre. Instead of being roughly aligned with the rotation axis, as it is for Earth, Jupiter, and Saturn, Uranus's magnetic field is tilted 59 degrees from the rotation axis and offset from the planet's center. This configuration creates a magnetosphere that wobbles wildly as the planet rotates, producing a magnetic environment unlike anything observed at any other planet. Voyager 2's plasma instruments measured the charged particle environment within this distorted magnetosphere and found radiation belts of unexpected intensity. The trapped particles within Uranus's magnetosphere were energetic enough to chemically darken the surfaces of the planet's innermost moons and ring particles over geological time. This process, called space weathering, was already known to occur at Jupiter and Saturn, but its intensity at Uranus was surprising given the planet's weaker magnetic field. At Neptune, Voyager 2 made discoveries that remain unmatched by any subsequent mission. The spacecraft arrived in August 1989 and found a dynamic, turbulent atmosphere marked by the Great Dark Spot, a storm system the size of Earth that has since disappeared. Neptune's winds were measured at speeds exceeding 2,000 kilometers per hour, the fastest wind speeds recorded on any planet in the solar system. This was deeply puzzling because Neptune receives far less solar energy than Jupiter or Saturn, yet generates more atmospheric activity. The energy driving Neptune's violent weather must come primarily from internal sources, heat left over from the planet's formation and possibly from ongoing gravitational contraction. Neptune produces approximately 2.6 times more energy than it receives from the Sun. Voyager 2 also discovered 6 previously unknown moons of Neptune and revealed that Neptune's moon Triton is one of the most geologically active objects in the solar system. Triton orbits Neptune in a retrograde direction, meaning it orbits opposite to the planet's rotation, strongly suggesting that Triton is a captured Kuiper belt object rather than a moon that formed alongside Neptune. Its surface, mapped by Voyager 2's cameras, showed active geysers erupting nitrogen gas and dark dust several kilometers into the thin atmosphere. The surface temperature was measured at approximately 38 Kelvin, making Triton the coldest surface ever measured in the solar system at that time. These observations from Uranus and Neptune are unique to Voyager 2. No other spacecraft has visited these worlds. No other mission is currently approved to visit them. Proposals exist, including the Uranus Orbiter and Probe mission recommended by the 2023 Planetary Science Decadal Survey, but such missions would not arrive at Uranus until the late 2030s at the earliest. For nearly 4 decades, and for at least another decade to come, Voyager 2's data from the ice giants represents the entirety of our direct knowledge of these worlds. Every textbook description of Uranus and Neptune relies on Voyager 2. Every model of ice giant atmospheres is calibrated against Voyager 2's measurements. Every proposed future mission to these planets uses Voyager 2's data as its baseline. This is what makes Voyager 2 not merely a twin of Voyager 1 but a uniquely irreplaceable scientific asset. Voyager 1 broke the record for farthest human-made object. Voyager 1 was first to cross the heliopause. Voyager 1 captured the pale blue dot. In the public imagination, Voyager 1 has always been the star. But in the scientific record, Voyager 2 has produced data that Voyager 1 simply cannot match. The ice giant encounters, the functioning plasma science instrument, the direct measurements of the heliopause crossing, the detection of the plasma leakage layer, the characterization of heliopause asymmetry. These are Voyager 2's unique contributions, and they are irreplaceable. Now, in 2026, both spacecraft face the same existential crisis. Their power is running out. The radioisotope thermoelectric generators that have sustained them for nearly 50 years are steadily decaying. The plutonium-238 that fuels these generators has a half-life of 87.7 years. After 49 years of operation, the generators produce less than half their original electrical output. Both spacecraft lose approximately 4 watts of power every year. The margins between operational power and the minimum required to keep critical systems functioning are measured in single-digit watts. Voyager 2 currently retains 3 working science instruments: the magnetometer, which measures magnetic fields, the cosmic ray subsystem, which detects high-energy particles, and the plasma wave subsystem, which detects vibrations in charged particles. The plasma science instrument, the very instrument that made Voyager 2's most important interstellar discoveries possible, was shut down in October 2024 to conserve power. The low-energy charged particles experiment was shut down in March 2025. Each shutdown was a calculated sacrifice, trading scientific capability for operational longevity. The engineering team at JPL has developed an ambitious plan to extend both Voyager's lifetimes. They call it the Big Bang. The concept involves simultaneously replacing multiple power-consuming components with lower power alternatives in a single coordinated operation. Rather than gradually shutting down systems one at a time, the Big Bang would reorganize the entire power architecture of the spacecraft in one bold maneuver, freeing up enough energy to keep remaining instruments operating and the spacecraft warm enough to survive the extreme cold of interstellar space. Voyager 2 has been selected as the test subject for the Big Bang. It has slightly more available power than Voyager 1 and is closer to Earth, making it the lower-risk candidate for testing an untried procedure. The tests are scheduled for May and June 2026. If successful on Voyager 2, the same procedure will be applied to Voyager 1 no earlier than July. The stakes are extraordinary. If the Big Bang works, it could extend both spacecrafts' operational lifetimes by years. If it fails, it could trigger cascading system failures from which recovery might be impossible. At a distance where commands take over 18 hours to reach Voyager 2 and confirmation takes another 18 hours to return, the margin for error is essentially zero. The irony of using Voyager 2 as the test subject for a potentially mission-ending procedure is not lost on the scientific community. This is the spacecraft that carries unique data from Uranus and Neptune. This is the spacecraft whose plasma science instrument revealed the plasma leakage layer and the asymmetry of the heliopause. This is the spacecraft that, in many ways, has contributed more to our understanding of the solar system and its boundary with interstellar space than any other single mission in history. And it is being used as the guinea pig for a risky engineering experiment because its slightly higher power levels make it marginally safer to test on. If the Big Bang fails on Voyager 2, the loss would be devastating. The spacecraft would likely enter a fault protection mode from which recovery would be uncertain. Its remaining instruments might shut down permanently. Its antenna might lose alignment with Earth. The faint radio signal that has traveled across 13 billion miles of void for 49 years might fall silent forever. And with it would go humanity's only direct connection to the interstellar medium through a functioning plasma instrument, the only spacecraft to have visited Uranus and Neptune, and one of only 2 human-made objects ever to have left the solar system. But if the Big Bang succeeds, the payoff would be enormous. Extended operations would allow Voyager 2 to continue characterizing the interstellar medium for years to come. Each additional year of data deepens our understanding of the environment surrounding our solar system. Each additional measurement constrains models of the heliosphere's shape, the interstellar medium's properties, and the dynamic interaction between them. Each additional day of operation is a day when humanity has sensors in the space between stars, collecting information that cannot be obtained any other way. The contrast between the 2 Voyagers highlights something important about how we explore the unknown. We tend to celebrate firsts. First to reach the moon. First to leave the solar system. First to cross the heliopause. Voyager 1 captured most of those firsts. But in science, firsts are not always the most important achievements. What matters most is understanding. And understanding often comes not from the first observation but from the second. From the comparison. From the ability to measure the same phenomenon in 2 different ways or from 2 different perspectives and discover what differs. Voyager 1 told us that the heliopause exists. Voyager 2 told us what it is actually like. Voyager 1 told us that interstellar space begins at a certain distance. Voyager 2 told us that this distance varies depending on direction. Voyager 1 told us that the transition is sharp. Voyager 2 told us it can also be gradual. Voyager 1 gave us the headline. Voyager 2 gave us the story. And the story is far more complex, far more nuanced, and far more scientifically valuable than the headline alone could convey. Both spacecraft continue to drift outward through interstellar space. Voyager 1 leads, approximately 15 billion miles from Earth, traveling at roughly 38,000 miles per hour. Voyager 2 follows at approximately 13 billion miles, traveling at roughly 35,000 miles per hour. Neither spacecraft will ever stop. Neither will ever return. Neither will ever be recovered or repaired. They will continue outward through the galaxy long after their instruments fall silent, long after their golden records become unplayable, long after the sun itself has exhausted its fuel and gone dark. They will drift through the interstellar void for millions of years, silent artifacts of a species that looked outward and wondered what lay beyond the next horizon. But right now, today, they are still alive, still transmitting, still detecting, still revealing the structure of a universe that is far more complex and far more surprising than any model predicted. Voyager 2's discoveries at the heliopause, its detection of the plasma leakage layer, its measurement of heliopause asymmetry, its characterization of the interstellar medium's density and temperature, these findings are unique. They exist because one instrument survived that should not have survived. They exist because a mission designed for 4 years lasted nearly 50. They exist because engineers at JPL refused to let their spacecraft die quietly and instead squeezed every possible year of operation from machines that have outlived every expectation placed upon them. The two Voyager spacecraft together represent humanity's most ambitious act of exploration. They have traveled further than anything we have ever built. They have lasted longer than anyone imagined. They have discovered phenomena that no one predicted. And they have done so on a combined budget that, adjusted for inflation, is less than what a single modern aircraft carrier costs to build. Two spacecraft, launched in 1977, still operating in 2026, exploring a region of space that no other human-made object has ever reached, carrying golden records that contain the sounds and images of a civilization that may not exist when those records are finally found, if they are ever found at all. Voyager 2 detected something in interstellar space that Voyager 1 missed. It detected the true nature of the boundary between our solar system and the galaxy. It found that boundary to be leaky, asymmetric, variable, and far more dynamic than anyone expected. It found that the interstellar medium is denser, warmer, and more structured than models predicted. It found that the space between stars is not empty but filled with plasma that carries the fingerprints of every star that has ever lived and died in our cosmic neighborhood. These discoveries were possible only because Voyager 2 carried an instrument that its twin had lost decades earlier. An accident of hardware failure that transformed an apparent setback into one of the most consequential scientific advantages in the history of space exploration. The space between stars is not what we thought. It is not a uniform void. It is not a passive backdrop against which stars and galaxies perform their cosmic theater. It is an active environment with its own structure, its own dynamics, its own weather. And we know this because a small spacecraft weighing less than a ton, launched nearly 50 years ago on a rocket that would be considered primitive by modern standards, carried a single functioning instrument into a region of space that no engineer who built it ever expected it to reach. That is the power of exploration. Not the power of speed or strength or overwhelming force. The power of persistence. The power of survival. The power of continuing to function, continuing to measure, continuing to transmit, long after anyone expected the mission to end. Voyager 2 has been humanity's quiet explorer, overshadowed by its famous twin, underappreciated by the public, but indispensable to the scientists who study the boundary between our solar system and the cosmos beyond. What it found there, in the darkness between stars, has changed our understanding of where we live and what surrounds us. And it is still out there right now, still detecting, still measuring, still sending its faint whisper of radio waves across 13 billion miles of void, telling us something true about a universe that we are only beginning to understand. So here is my question for you in the comments. Voyager 1 gets all the fame, but Voyager 2 made the discoveries that actually changed our understanding of the solar system's boundary and the space between stars. Which spacecraft do you think contributed more to science and why? And here is a deeper question. If the Big Bang maneuver fails and Voyager 2 goes silent forever, what will we have lost? Is it just a spacecraft? Or is it something more? Is there something about having a human-made object out there, in the space between stars, still sending signals home, that matters beyond the science it produces? Let me know your thoughts below. I am genuinely curious about your perspective. Let us discuss it together.